Alright, so before we get into the actual exercises of Chapter 9 here of the addition and subtraction of fractions, it's important to maybe review or kind of expand the toolkit for what we're going to be using for these exercises. So I just have a few operations here put up, and knowing the fraction rules that go forward here is important for solving the exercises. So we'll start out with a quantity x over y plus a quantity z over y. If you notice, these have common denominators, and what that allows us to do, their addition, y is going to remain as the denominator, and all I have to simply do is add x to the z in the numerator, because the denominator is the same, the operation carries over. So simply, it's just x plus z over y. And if you notice, we can split that up and revert back to our original equation here. And the same thing follows for common denominators of subtraction. The operator is subtraction, and in this case it's simply just going to be x minus z over y. And that leaves us with what to do when the denominators are different, and this is where you have to start multiplying terms and figure out what the common denominator is. So the common denominator of any n terms is the multiplied string of n denominators. In this case, there are two denominators, so we're multiplying y times w. And that's the common denominator. But now we have to figure out how to express x and z in the numerator of this now common denominator. And the rule for that is you take the numerator of the first and multiply it by the denominator of the second, so x times w. And then the operator maintains, plus, and then it's the denominator of the first multiplied by the numerator of the second, so y times z. And that is the expression of x over y plus z over w combined into a single fraction. And what's nice about addition and subtraction is they're essentially the same operators, so the rule of these operators carries forward. So when we have a quantity x over y minus z over w, the denominator is simply y times w again. And really the only difference is the operator. Numerator of the first multiplied by the denominator of the second, x times w, minus subtraction operator, denominator of the first multiplied by numerator of the second, y times z. And these are essentially the basic steps for addition and subtraction of two fractions, and you can carry this over to however many fractions that you are combining into a common denominator. You just have to take it one step at a time to do so. So simplify 2 into 1, and then move on to the next one to finish out n terms to a common denominator. So these are all going to be super useful for the exercises moving forward, so it's very important to just get a little review in so we understand these. Alright, so here we go. First example from Chapter 9 of Euler's Elements of Algebra of the addition and subtraction of fractions. So here we have to reduce the quantity 2x over a and b over c to their common denominators. So the general rule, we know that each of them, we don't know exactly what the numerator is going to consist of, but we know that the denominator is simply going to be a times c, because they both need to satisfy their common denominators. So how do we get from 2x over a to a denominator with a times c? Well, clearly we have to cancel out a c to be able to revert back to our 2x over a quantity. So simply all we have to do is multiply 2 times x by a c, and as you'll notice, if those are canceled out, we'll revert back to our original. So that's done. And now we have to find out how to get b over c to satisfy our common denominator of a times c. We already have a c in the denominator here, so clearly all we need to do is multiply an a in both numerator and denominator, and we are left with a times b over a times c. They have common denominators, therefore they have been reduced to their common denominator. Alright, and here's example 2 from the same chapter, which is reducing a over b and a plus b over c to common denominators. Multiplying the denominators of everything we need to reduce to a common denominator, we are left with b times c. So all we have to do now is figure out how to get these two into that form of denominator. So a over b. It's pretty clearly seen here that all we need to do is multiply a c within this fraction here. So a times c over b times c. So that's done. And now the second one, a plus b over c. How do we get that to a denominator with b times c? Clearly there's a b here that we need to multiply in. So remember, distributing the b into the a plus b in the numerator here, that's multiplying a times b plus b by itself. So we're left with b times a plus b squared, which is the form that Euler wants us to seek, but we know that this is equivalent to b times a plus b over b times c. And these have been reduced to their common denominators. And this brings us to question 3 Euler provides for us, which is reducing 3x over 2a, 2b over 3c, and d to common denominators. It's helpful to note that d here is the same as d over 1, which helps us because now we know that the common denominator for these three quantities is going to be 2a multiplied by 3c multiplied by 1, because that's the denominator in d here. So our denominator is going to look like 6 times a times c. Now all we have to do now is find out how do we get the denominator of this sort in equality with the terms we need to reduce. Starting with 3x over 2a, we know that we have to get the denominator into the form 6 times a times c. So what do we have to multiply 3x by to be able to cancel out with these terms here to revert back to our 3x over 2a? So realizing that the ratio of 3 to 2, the constant in this is going to be 9 because that follows the same ratio of the original quantity. Obviously we're going to still have our x. We need a c here, as those will cancel out and revert back. And clearly that's all we need to do for this one, because adding an a up here would cancel out, which doesn't get us back to our original quantity. So this one is done. 2b over 3c. We know that we need the denominator into the form 6 times a times c. So what do we need to multiply 2b by to cancel out in this full denominator here to get back to 2b over 3c? Well, the c is already there, so we know that that's going to be alright. So we need to definitely multiply an a here. The b is definitely going to be in the numerator as well. And to keep our ratio of 2 to 3, what is 2/3 of 6? That is going to be 4. So 4 times b times a. And if you notice, the a's will cancel out. These will simplify down to 2/3, and all we would be left with is 2b over 3c. So that one is done, and we'll put d in this form, d over 1. How do we get that to 6 times a times c? Well, simply all we need to do is multiply it by the full denominator here, because if you notice, the denominator has no d variable in it, so we need all of these to cancel because we revert simply back to d. So d times 6 times a times c. And now we have all of these in their respective common denominators, and we are done. These are the quantities Euler wanted us to seek. This brings us to our fourth example Euler provides for us, which is reducing 3/4, 2x over 3, and the quantity a plus 2x over a to common denominators. First of all, what's very helpful to do when reducing three terms is if they were all in fraction form. Clearly a plus 2x over a is not in one single fraction, so let's go ahead and do that. A plus 2x over a. We know that a obviously is just equal to a over 1 plus 2x over a, which helps us for combining these into a single fraction. The rule is, in the denominator, denominators obviously multiply together, so 1 times a is simply just a. we know that the numerator of the first and the denominator of the second need to be multiplied together. And the numerator over here, so a times a squared, plus, likewise, denominator of the first term needs to be multiplied by the numerator of the second, 1 times 2x, a squared, plus 2x over a. So now we know that the three terms we have are a squared plus 2x over a, 3/4, and 2x over 3. So this tells us the denominator that we're seeking is going to be multiplying these three denominators together, which is a times 4 times 3. 4 times 3 is 12 times a, 12a. So that's the denominator that our terms are all going to be reducing to. So let's start with 3/4. How do we get that into a form where the denominator is 12a and we can reduce down to 3/4? Well, if 12a is equal to 4, 3/4 of 12a is simply going to be 9a, because the a's will cancel, and 9 over 12, 3, 6, 9, 12. So 3/4, that's done. Second one, 2x over 3. Knowing the denominator is 12a, what do we have to do here? Well, so first of all, noticing the constants in our original term here, 2/3. What is 2/3 of 12? Dividing 12 by 3 is 4, so 2/4 is 8. Clearly there's an x in this term that doesn't get canceled out, so the x will stay. No a term in the original, so that will cancel out. And that's done because that isn't complete. And our new fraction we've combined here is a squared plus 2x over a. How do we get that into a form where the denominator is 12a? Well, simply because the denominator clearly just has a 12 multiplied into it. All we have to do is multiply a 12 into the denominator, because there's no constants in here, which means they were all reduced to a constant of 1, which means that the 12 is going to cancel out. So multiplying a 12 through to a squared plus 2x, we have 12 times a squared plus 2 times 12 is 24 plus 24x. And as you can see, this is the quantity Euler wants us to seek. But for us, for the sake of ease of factoring out later, if we were ever to go back into these terms, we are just simply left with a squared plus 2x multiplied by 12 over 12a. And it's quite apparent that simply canceling out a 12 here will revert us back to our original quantity. These all have the same denominator, therefore they have been reduced to their common denominators. And this question is done. All right, and this brings us to the fifth question Euler provided for us, which is reducing 1/2 a squared over 3 and x squared plus a squared over x plus a to their common denominators. So what's nice about this one, these are all in one single fraction, so I can simply multiply their three respective denominators together to form our common denominator. So we know that it will be 2 times 3, which is 6, multiplied by x plus a. So we're left with 6x plus 6a as our common denominator. So now all we have to figure out is how to reduce or expand our three quantities here into this denominator. Starting out with 1/2. How do we get that into denominator of 6x plus 6a? Well, really all we need is a ratio of 1 to 2, so a half. What is a half of 6x plus 6a? A half of 6x plus 6a is going to be 3x plus 3a, because half of 6 is 3. 3x plus 3a. If you notice, if we were to reduce that, we would return to our original quantity here. So that's done. A squared over 3. Alright, with a denominator of 6x plus 6a here, what do we have to multiply the numerator by to be able to cancel out and return to a squared over 3? Well, the constant ratio here is 1/3. So what is 1/3 of 6? That's going to be 2. We realize an a squared will remain in the numerator once everything cancels out. And we also have to notice that there's an x plus a now introduced in the denominator. So that x plus a is going to be canceled out to be left with an a squared in the numerator. So the way that we can formulate this, again, we know that 2 is 1/3 of 6. So an x is definitely going to cancel because of the 6x in the denominator here. And this a squared is going to remain. And also, there's no x in the second term here because we want that to cancel out. We want to be able to pull out an x plus a and cancel that out. So what we're left with here is simply just a 2a cubed because we still want an a squared here, and we need to still factor out an a in order to have our x plus a factored out. So we need to have 2a cubed there in order to remain consistent and reduce down to a squared over 3. And that has been reduced. And x squared plus a squared over x plus a. Well, at first seeming a bit complicated, it's fairly easy to realize that simply all we're doing here is we're multiplying a 6 into the denominator here, and we want that to factor out and cancel out to be able to revert to our x squared plus a squared over x plus a. So all we have to do is multiply everything by 6 here. And now these denominators are all common to each other. Therefore, they have been reduced to their common denominators, and these are the quantities Euler wanted us to seek. Alright, and this brings us to the final example Euler provided for us here in Chapter 9 about reducing to common denominators. So we got 3 quantities here, b over 2a squared, c over 2a, and d over a. So if you notice, there's actually 2 different methods or end results that we could seek out for an answer here, of which Euler also recognizes there are multiple. And if you realize looking back at many of these problems, there's actually infinitely many different common denominators that you can express with 1, 2, 3, up to infinity different terms, just because for the same reason that you can express 1/2 in infinitely many ways, such as 2/4, 3/6, etc., etc. So, without going too over it, essentially there are 2 different common denominators that Euler provides for us to seek here. And the first one is just going to be simply the same strategy we've been using before, which is multiplying out all of the denominators and then forming our common denominator via that one given. So if you notice, 2a squared times 2a, 4a cubed times a, 4a to the 4th power. But you might have already noticed that 2a squared, for our first term here, that is actually a common denominator that we can also seek. And why is that? Because our remaining 2 fractions, c over 2a and d over a, multiplying their 2 denominators leaves us with a 2a times a, which is 2a squared, which means that they can be expressed in the same denominator that our first term is. So, starting out with our first method, how do we get b over 2a squared into the form with a denominator of 4a to the 4th power? Well, it's fairly obvious that 2a squared was simply doubled here, and we want our b term to be remaining, so b times 2a squared. So as you'll see, a 2a squared will cancel out, and we'll revert back to our original quantity. c over 2a, how do we get that into form with a denominator of 4a to the 4th power? Well, the denominator has to be multiplied by 2 and an a cubed, so that must mean we multiply the numerator by that. So, c times 2 times a cubed. If you notice, those will cancel out and revert back to our original quantity. d over a. How do we get that into the form 4a to the 4th power? Well, simply multiplying it by 4 and an a cubed. d times 4 times a cubed. And if you notice, those will factor out, cancel, and leave us with our original quantity. So that is the first method, of which the common denominator is 4a to the 4th power. But let's say you were smart enough to save some time on a test or whatever, and you realize that we can just convert c over 2a and d over a into this b over 2a squared common denominator. So b over 2a squared obviously is going to remain the same. c over 2a, how do we get that into a form of 2a squared? Well, fairly obviously, all they did is multiply by an a in the denominator, so that's what we must do in the numerator. C times a, and then d over a. Clearly, we just multiplied the denominator by a 2 and another a. So d times 2 times a. And these have all been reduced to their common denominator with a denominator of 2a squared. And that's going to do it for this final problem. So there are two solutions Euler provides us for this exercise. One is simply just dependent on realization that, hey, we can form a common denominator out of one already provided for us with the remaining two terms. And that can be done of any number of terms of fractions that you need to combine into a common denominator. If you can morph them into simply one of the denominators already provided, most of the time it's much easier to do that. It becomes more obvious, at least, what you should multiply out to get to our common denominators. Fraction manipulation is extremely important in high-level maths as you're working through some very, very messy equations and problems. So it's very important for you to be able to offhand and essentially immediately be able to manipulate and simplify or expand fractions in terms together or apart. And obviously this is why Euler stresses these exercises so much. So that'll do it for our Chapter 9 exercises for Euler's Elements of Algebra here, of the addition and subtraction of fractions, where we just went over the reduction of any number of fraction terms up here. For Euler only provided us with up to 3 different quantities to reduce to a common denominator or to expand to a common denominator, which is really what we've been doing this whole time. But again, very important for you to be able to quickly manipulate, simplify, or expand fractions to common denominators. Thankfully, Euler provided us with these exercises. Thank you for watching. Have a wonderful day, evening, whatever.